Hello, in this video we will talk about the Nernst equation. So the background here is that the sign of E cell gives us spontaneity. We talked about this in a previous video. If E cell is positive, then your reaction is spontaneous, it goes to the right, as written. If it's negative, then your reaction is not spontaneous, and it goes to the left. Now, if E cell can predict spontaneity, then it has to be related to delta G, the Gibbs free energy, which also predicts spontaneity. And indeed it is, and so here's the equations for that. You have the Gibbs free energy change, you have NF E cell, and we'll talk about what those are in a minute. Well, you know what E cell is. And then this is true with or without the degree signs, and so delta G naught is equal to E naught cell. And the difference between the degree signs or not has to do with your concentrations. At standard states, that means you have 1 molar solution concentrations or 1 bar of gas pressure, and then that gives you delta G naught, which tells you the same thing, is it spontaneous under those conditions. And without the degree sign, well, then it's true for any concentrations. So N here is the number of electrons that are transferred. So if you think back to when you're balancing the redox reactions, the last step you had to adjust both half reactions until the number of electrons is the same, and that number of electrons is N. Now, your textbook calls this nu subscript E. Nu is the Greek letter that's closest to N to our eyes. But I don't like that. I don't use nu E because most places I've seen just use N. So I'm just going to use N, and everyone in our department does the same thing pretty much, so that's fine. Then F is a new constant. It's called the Faraday constant. And this is the charge on 1 mole of electrons. And so our unit of charge is coulombs. This is moles, okay? This is 96,000 coulombs per mole. And then you can rephrase a coulomb as a joule per volt, which the units here work out better for what we're trying to do, because coulomb is defined as a joule per volt. And then moles is also in the denominator. All right, so we have our connection between delta G and E cell. Now the next thing we can do is compare E naught cell, standard states, to K by using these two equations. This is the one we just introduced. Here's one from a few chapters ago. Hopefully it looks familiar. And then if we set the delta G naughts equal to each other, you get this. Okay. And then you rearrange it to solve for E naught cell, and this is called the Nernst equation. And so this relates E naught cell and K, which, I mean, you could do a 2-steps process, right? Go E naught cell to delta G naught, and then go from there to K, but this basically combines it together and makes it 1 step. Again, the degree sign here matters a lot. E naught cell is standard cell voltage, where all solutes are 1 molar, gases are 1 bar, and these standard voltages are what you find listed in the table. So if you're going to calculate E naught cell, you can just pull the data out of the table, and that's great. If you're not at standard states, then you can't use the tabulated values. You can go measure it, but it's a little more complicated to do that. Not really complicated, just takes time. Okay, another thing we do is, since we're usually at 25C, we can just plug in R, it's a constant, T, 298 Kelvin, F, Faraday's constant, and just combine all these constants together, and then we get this form. This is kind of the lazy person's way to do it because, I mean, you don't have to plug stuff in except for N, which changes depending on the reaction, and so this works too. I've also seen this written not with a natural log, but with a base 10 log, and there's a conversion factor between the two. It's about 2.3 or so. So you'll see this with base 10 log, log, and then a different number for the combined constants. And it works just the same. Okay, so here's a little summary showing how to get where you want to go. If you're at E naught cell, well, you can use the Nernst equation to get K. And then from a few chapters ago, right, you can go from K to delta G naught. And then you can use the equation we introduced at the beginning to get back up to E naught cell. So you can go around any which way you want. If you're trying to convert between these values, it's all equivalent. All right, let's try this. So let's find the equilibrium constant for this following reaction. It needs to be at 25C because we're using these tabulated values. Remember, standard states does not define a temperature, but the stuff in the table does. Here's the Nernst equation we're going to use. We can start with the lazy version. Now we have to find E naught cell. So when we did this in a previous video, we looked at the numbers in the table, and we left the reaction on the top the same, and we flipped the one on the bottom. And we were doing that when we were asked to just make a spontaneous cell with a positive E naught cell, given these two half cells. Like, we could rearrange them however we wanted. But that's not what we're doing here. Here we have an equation up top, and we're going to rearrange these to match the equation. And so if you look at this, the silver is oxidized, and then silver is written as a reduction potential here, and it's higher on the list. So this tells us if we flip the one higher on the list, we're probably going to have a non-spontaneous reaction. But we'll see how it goes when we get there. So, because the silver is oxidized, we have to reverse this half reaction. And once we reverse the half reaction, we change the sign on E naught. And the fact that there's a coefficient of 2 here doesn't change E naught at all. It's an intensive property, so it doesn't depend on the amount. All right, we can leave the iron 2 plus well alone, because in the equation it's going from 2 plus to 0. It's the reduction, and so we can just pull this straight out of the table. Now we're going to need to know the number of electrons transferred, and it's 2, because you just pull it right out of the two half reactions like this. All right, so here's our equation for getting E naught cell from the reduction half reaction potential and the oxidation half reaction potential. And we already converted from reduction in the table to oxidation, so we don't need to mess around with this again. So we just plug those numbers in, and we get negative 1.24 volts. Like we suspected, this is not spontaneous because we reversed the reaction higher on the list. That's because we were told to do so by this reaction. You can write whatever the heck reaction you want, spontaneous, not spontaneous. You can write it and do the math on it. It's just going to go to the left and not the right. Okay, so we're in the business of finding K, and so K is up here, and we have E naught cell. So we need to solve for K, so we'll multiply N on both sides to move it up here. We'll divide both sides by the constant. Then to get rid of the natural log, we take E to both sides. So that gives us just K on one side and E to all the stuff on the other side. So it looks like this. Now, let's plug some numbers in. All right, here's our E naught, our cell potential under standard states. Here's N. And when you solve this, you get a really small number for K. And so this tells us that the equilibrium position lies far to the left, which we would expect because the E naught cell is negative and fairly large. So that means that's also non-spontaneous. So these two give you complementary information that says the same thing. All right, one more example. So now instead of solving for K, we're going to solve for the free energy change. So this is delta G naught. And we have this reaction. And it looks like the one on the last slide, but it's different. You can still use the same set of reduction potentials. But here, instead of silver being oxidized, the silver is reduced. So that means we can just use the one on the top without flipping it. And now we have the different form of iron. So we can go from iron 2 plus to iron 3 plus. So that's this reaction in the middle, 3 plus to 2 plus, and we'll have to flip it. So we'll see that in a minute here. Here's kind of the equation soup for what you might want. You're going to need these three, right? You're not going to use the Nernst equation because we're not trying to find K. Okay, so like I said just a second ago, we're going to wind up using the top standard reduction voltage as is because we go from positive to neutral here, so we just use this as is. Then we got to flip this one because we go from iron 2 plus to iron 3 plus in the reaction up top. And so that means we change the sign on this from positive to negative. Then once we do that, flip the reaction and change the sign, then we add them together. While we're thinking about it, we should point out that N is equal to 1 in this reaction because there's one electron on both sides. Okay, so now we add these together and we get 0.03 volts. So this tells us that it should be spontaneous under standard states if you have 1 molar of everything. But it's going to be barely spontaneous because it's a small number. All right, so now that we have this, we can use the equation and figure out what delta G naught is. And so we plug stuff in. Here's N. Now N is not negative. I just kept the negative sign from up here and didn't drop it. So here's N. Here's the Faraday constant. You want the version in joules per volts mole because that will cancel out the volts and it'll give you joules, which you want. And here's E naught. And so you calculate this out. And to the sig figs we have, it's negative 3 kilojoules per mole, which is spontaneous. A negative delta G naught says that if you have 1 molar of everything, it's going to the right. This is a really small delta G naught compared to other ones we've calculated, which kind of goes along with what we said, that this will be spontaneous, but barely, because this number is small, this number is small. So it'll still go to the right, it just won't go very far before it stops. Cool, that's all I have for this video. Thanks for watching.